Swayam Prabha. Digital India. Educated India.
Vx is the potential at a distance x away from the source region. This is the channel potential. Based on this, the drain to source current IDS at x is given by QDX multiplied by velocity of the carriers V, and velocity V is specifically for electrons is given by minus mu n times E. E is the electrical field, and electric field is in this particular case is given by minus mu n times minus dVx divided by dx, and that comes out to be, again the two negative signs go away and you get mu n dVx divided by dx. So this is the velocity of the electrons, because electrons are the carriers in this case. So the signs basically take care of electrons and specifically for electric field based on the delta of the potentials. So we can then write expression for IDX as function of x is given by W Cox VGS minus Vx minus Vth, and velocity is given by mu n times dVx divided by dx. So we can adjust this equation and you will get IDS as function of x times dx is equal to W Cox VGS minus Vx minus Vth times mu n times dVx, V being the potential. So we can integrate both sides, and the left side of integral has dx in it, so it will go from x equal to 0 to, we are going from source region to the drain region. So we are going from x equal to 0 to x equal to L. And on the right side we have potential Vx. When we go from x equal to 0 to x equal to L, which is source to drain region, the potential Vx is going to will go from 0 to Vx equal to Vds. So we can write we can do this integration and you will see it becomes IDS times L, dx becomes L after integration, and on the right side you get 0 to Vds mu n W Cox VGS minus Vth minus Vx dV, and this would look like mu n Cox, and this part will give us VGS minus Vth times Vx minus Vx square divided by 2, and this would go from 0 to Vds. So if we substitute in the integral, what we will get is IDS is equal to, I'm going to move this L to the right side, so this will become mu n, which is mobility of the electrons, W divided by L, mu n Cox W by L. Okay, so this is the final equation for drain to source current when VGS is greater than Vth, and we have an inversion layer formed and we have drain to source potential applied. The key thing to note here is the insides part is IDS, which is drain to source current, is proportional to mu n, which is mobility of electrons, the Cox. So if we increase Cox, which means if we decrease the Tox, thickness of the oxide region, then the drain to source current increases. Other thing is W by L ratio. This is called actually device aspect ratio. So W by L, if you increase, which means if you reduce channel length and if you increase channel width, then the IDS will increase proportionately. Other part here also we know that the drain to source current is proportional to VGS minus Vth. So higher the VGS compared to Vth, the current will be higher. Also the drain to source current is proportional to VDS. Increasing VDS will increase the drain to source current, and this is valid for VDS less than VGS minus VTH. Let me show you where this comes from. If you look at this particular expression, which is inside, we can say that if VGS minus VTH times VDS is much greater than VDS divided by 2 square. If that is the case, then you can see that the IDS will be proportional to VDS. And this is what gives you the condition which is described here. This tells you that VDS has to be less than 2 times VGS minus VTH. So under this condition, your IDS is going to be equal to mu n Cox W by L times VGS minus VTH times VDS. So let's try to draw this particular curve IDS. If you look at the expression for IDS, that looks like an expression for a parabola. What we are plotting here is VDS on the x-axis and IDS on the y-axis. For different values of gate to source voltage, let's say VGS1, then we will see the parabola would look like this. This point would be VGS1 minus VTH. And our characteristics is going to look like this. And the part we don't know is what happens out on this side. Similarly, for different value of VGS2, if VGS2 is greater than VGS1, then we would expect to see something like this. And this being VGS2 minus VTH, then the parabola would look like something like this. Again, we are plotting the curve when VDS is less than VGS minus VT. If we look at this expression, IDS mu n Cox W by L VGS minus VTH times VDS. This is valid when VDS is smaller than 2 times VGS minus VTH. So this we can draw model that looks like this. This is our MOS device and we are applying a fixed VGS and we are applying VDS here. This is the way it looks like. If I change VDS, there is a current which is IDS flowing. We can look at how much the variation in the current IDS is and what would that give us. So what I'm looking for is del IDS by del VDS, and that will be equal to, since we have fixed VGS, this is going to look like mu n Cox W by L times VGS minus VTH. And here you can see everything else here is a constant because we are setting VGS to certain value. And the one expression that we are plotting, trying to find out here, if we take inverse of that, that will look like resistance of the device. R on equal to del IDS by del VDS inversion. So this is going to look like 1 over mu n Cox W by L times VGS minus VTH. So we can quickly see now for a given VGS, resistance looking into the drain, between drain to source region, R on is fixed. So the device looks like a resistance as long as VDS is small value. The original assumption that we had, VDS is small compared to VGS minus VTH, much smaller than VGS minus VTH. So we say that this is a linear region of operation. So this resistance, since it looks like a resistor, we say we have a resistance between drain to source. The value of the resistance can be changed by controlling VGS. The transistor is operating in the linear region, also called as triode region. So what we have learned so far is the transistor equation based on the carrier transport is given by, and we say that if VDS is small, then the resistance looking into the drain to source region looks like a constant value, which is reciprocal of mu n Cox W by L VGS minus VTH. And since it looks like a resistor, we say that the transistor is in linear region or triode region. So in the previous discussion, we said that the drain to source voltage VDS is much smaller than VGS minus VT, and that's when we call the transistor to be in triode region or linear region. Let's draw a profile of the NMOS transistor and let's see what happens when we start increasing the drain to source voltage while the channel is formed. If you remember the expression for the channel charge, QD as a function of X, it is given by width of the device, oxide Cox, and then VGS minus Vx minus VTH. So when we are looking at the source region, we are close to source region right here, then the channel charge is going to be VGS minus VT times WCox. So there is always, you need the VTH is what you need to cause inversion and get the charge under the channel. If you just have a simple capacitor, okay, then the charge value is given by C times V. So if you apply a potential plus minus V, then the charge on this negative terminal will be C times V. In the MOSFET, because of the threshold voltage, we have to subtract the threshold voltage out to figure out the value of the charge. So in the case of MOSFET, Q is given by C times V minus VTH. And I think once you understand this part, rest of the things will fall in place. And that's where this minus VTH comes in. However, the voltage at the channel, if we look at the different points in channel, I'm going to show you different arrows. The first arrow, what is the channel voltage, is going to be VGS minus VTH. And the channel voltage at this point is going to be VDS because we are at the drain region. So Vx is changing if we plot it on this axis right here. Let's say this is our 0 and this would be L. Vx is changing from 0 to VDS. That's what is going on. X is in this direction for convenience. Now we can write based on this understanding that QD W Cox VGS minus VTH. I'm just arranging the term for clarity in this way. So when X equal to L, what is QD? QD at L is equal to W Cox VGS minus VTH minus VDS. So QDL is a channel charge at X equal to L. A crucial observation is what happens at VDS equal to VGS minus VT. If we look at this particular expression, you can obviously tell that QDL becomes equal to 0. Now we can draw it on our cross section here. It would look like this. So these are all electrons here. So when VDS is equal to VGS minus VT, then the channel charge at this point has gone to 0. What does that really mean? This point is called pinch-off point. The channel is pinched off when VGS minus VTH equal to VDS. VDS is equal to VGS minus VTH. Channel is pinched off. Now what happens if we keep increasing VDS beyond VGS minus VTH? You would expect that this profile would change in this fashion. Look at the yellow now. So the channel pinch off will happen slightly earlier. And this should remind you of the effect we saw in the bipolar region. In the bipolar device, when you have base to collector junction that is reverse biased, then the width of the base reduces. Something similar is happening over here. we have depletion region at the drain of the device, as a result of which, after pinch off, when VDS is greater than VGS minus VTH, we have a depletion region formed in the magenta region. So redrawing here, we would see when VDS is greater than VGS minus VTH, we would say that the channel would terminate earlier somewhere over here like this at a point L dash, which is smaller than the original channel length L. So what's really going on here is we have a depletion region around the drain, and the depletion by definition means there are no carriers. So we have a very strong electric field in the depletion region, as a result of which the electrons which are coming at high speed from the source region, they are swept away across this depletion region like this. So the electrons will shoot through the depletion region and they will arrive at the drain. The carrier velocity of the electrons will increase a lot. So the velocity V, which is equal to drain current divided by QD. So this will increase. Let's try to formulate current expression when the transistor is in pinch off and beyond. So let's come back to our original expression. I'll rewrite it. So pinch off and beyond, we will go from x equal to 0 to x equal to L prime. L prime being this particular dimension here. Bear in mind that L prime is very close to the channel length L. It's just slightly short. And on the right side, what is Vx varying from? Vx equal to 0 all the way to Vx is going to VGS minus VTH. And this happens because the channel gets pinched off when the channel potential is equal to VGS minus VTH. So if we solve this, we should get IDS times L prime is equal to mu n W Cox times, and this integral will go from 0 to VGS minus VTH. So this we will get it as IDS is equal to, and this expression will become, you can quickly see it's VGS minus VTH square. Again, L prime is the location where channel is pinched off. For all practical purposes, we use the actual drawn channel length L dimension instead of L prime for first order calculations. L prime is pretty close to L. So what's the key observation from this equation? The drain to source voltage VDS is greater than VGS minus VTH. Then there is no dependence on the drain to source voltage. The current IDS is independent of drain to source voltage. So in a way it looks like a constant current source independent of drain to source voltage. You can also say that the current is saturated. It doesn't depend on drain to source voltage anymore. Hence, this region is called saturation region. VGS minus VTH is called overdrive voltage or VD-SAT. This is just a terminology that everyone uses. So I'm just slowly making you familiar with all these names. And once we go through it many times, it will become second nature to you. So we also say that when VDS is greater than VD-SAT, the transistor is in saturation region. Let's go back to our transistor characteristics and see how this plugs into the curves that we drew earlier. Again, I'm drawing VDS on the x-axis and IDS, which is drain to source current, on the y-axis. And These 3 points are VGS1 minus VTH. The second one is VGS2 minus VTH. And third one is VGS3 minus VTH. To visualize, I'm going to give you a picture here. We are applying VGS and this is what we are plotting, VDS. And we are measuring how much is the current IDS. So when VDS is less than VGS minus VT, which would be the left portion of the curve, which we plotted in the first case, it looked like this. It looked like the inverse parabola. And this is the region we called earlier triode or linear region. The reason we call it linear because the transistor from drain to source looks like a resistance which is independent of drain to source voltage to a first order. On the right side of this curve, we can see that when VDS is greater than VGS1 minus VTH, the channel is pinched off and the channel current becomes independent of the drain to source voltage, as a result of which it just stays flat. Current will stay flat, and here also the current will stay flat, and same thing happens over here, the current stays flat. And these are our curves for VGS1 applied, VGS2 applied, or VGS3 applied, gate to source voltage. So if you look at the circuit diagram, we are increasing the VGS. When VGS increases beyond VTH, the threshold voltage of the MOSFET, we have a channel formed under the gate and the current will start flowing from drain to source if the drain to source voltage applied is positive. For VGS1, VGS2, VGS3, 3 different voltages, we will see increasing current flowing through the device IDS in saturation mode, independent of the VDS. And that's what is plotted over here. The right side of the curve, since the current is saturated, it's called current is saturated and is independent of the drain to source voltage, VDS. Hence, it's called saturation region. And left side of the curve is called triode or linear region. Since the right side is called saturation, the left side also many times is called non-saturation region. Okay. So this is the operation of MOSFET in 2 different regions. This looks very familiar to the curves that we plotted in the bipolar case. Throughout the rest of the course, we are going to always compare between different devices, BJTs and MOSFETs. We will do many circuits and we will continuously do the comparison. And here is your first comparison. In the BJT case, let's draw it on the right side. If you remember, so in the BJT case, again here in this case, as I have shown in the circuit diagram, on the x-axis we are plotting VCE and on the y-axis we are plotting collector current IC. If you remember, if VC is small, something like 0.2 to 0.3 volts, then the device is in saturation region. So these are different points. This is, let's call it 0.2 volts maybe. And for different values of VBE, we get more and more current flowing. So for example, we have a curve that looks like this. So all these curves are really sharp. If VC is greater than 0.2 volts, then the transistor is in active region. And in that region, the collector current is fairly independent of VCE for different values of VBE. So this is VBE1 and this is VBEN. Let's do another comparison between the 2 devices to put it all together. One more thing here is just to define the region. This is called active region and this is called saturation region. Now this nomenclature is going to be quite confusing. So let's put it out on a piece of paper so that we are all convinced about this. as a comparison between bipolars and MOS. So what I'm showing here is, on the left side, there are two regions of operation where device acts like a switch or a resistor, and for bipolar, that happens to be the saturation region. In this case, VCE is less than 0.3 volts or 0.2 volts, and if VCE is greater than 0.3 volts, then we call it active region, 0.3 volts being the edge of saturation. 0.2 volts or 0.1 volts would be deep saturation. So that is about bipolar device. In case of MOS, when VDS is less than VGS minus VTH, then we call that a linear region or triode region or non-sat region. And when VDS, drain to source voltage, is greater than VGS minus VTH, greater than or equal to, then we call that pinch off region, when the channel is pinched off, but we label it as saturation region. So this is a comparison between bipolar and MOS operating under the same type of operation. Key thing to note here is definition of saturation region. In MOS versus bipolar is completely flipped. In bipolar case, it's when VCE is less than 0.3 volts. When the device acts like a switch, then it's called saturation. Whereas in MOS case, it's the useful when the device is useful as an amplifier, we call it saturation region. When VDS is greater than VGS minus VTH. You may ask me why this is the case. The only answer I can give you is it is what it is. It's something that people have been using for a long time. If you do enough design with bipolars and MOS, then you get used to it. One more point I would like to make as a comparison between bipolars and MOS is the following. In bipolar, if you remember, the way we drew the device is the following. There is an emitter region, and then there is a base region, and then there is a collector region. Emitter, base, and collector. In case of MOS, on the right side, it's this way. In case of bipolar, the current is flowing in this direction, the IC for NPN. As you can see, the current is flowing vertically, and the reason we get bipolar effect or amplification effect is because the width of the base is extremely small. It's like a sliver, if you remember the operation of bipolar, right? And that's what gives us the gain effect. Now, this width of the bipolar region is really not controllable. Once you have a particular process, it's fixed. Only thing we can change is the area of the emitter, and that will change the property of the bipolar. So here we can also say that the transistor action is vertical. In case of MOS, we just reviewed that. This is our drain region, source region, and the current is actually flowing in this region. It's in this way. So the current is flowing laterally. We can change the dimension of this device, we can change the width of the device, and we can change the length of the device. And we can control the property of this MOSFET very well by doing these two things. So MOSFET offers you a lot more degrees of freedom in that sense, width and length of the device to change the current. In case of bipolar, the only thing we can do is change the area of the bipolar. Each bipolar will have exact same property, whereas in this case we have a lot more control. Thank you.